Hello, everybody. Wow, that changed my spot. This is Mr. Folly, and welcome to the last part of 1.7, where we will talk about trends and explain trends in the periodic table. So let's hop to it. All right. Next, one we're going to talk about is electron affinity, EA. Electron affinity is the ability to attract free electrons. Now, free electrons might seem weird to you, but if you've ever done the little boot scoot across the car, I guess it has to be boot scoot, but across the carpet, and you get all the electrons, you touch somebody and go, and they get shocked. Those were free electrons you picked up, and then electrons that you distributed to them. So that's the zappity zap zap you might be aware of. Okay, so electron affinity is the ability to attract free electrons, and it's abbreviated EA. EA increases going to the right. Dun, 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 going to the right, going to the right, going to the right, going to the right, going to the right. Because it has more attractive protons. So notice this has 3, this has 10, that's more. If you have more attractive protons, those attract the electrons, making it easier to attract free electrons. So there's more attractive protons. So if I'm more attractive, I pick up more electrons. How you doing? And all the electrons think I'm attractive. Oh yeah, they do. EA increases going up. Bum, 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 bum. Okay. Because the size is much smaller due to fewer energy levels or shells, which makes the attraction of the nucleus greater and makes it easier to attract free electrons. So this explains why it works going up and why it works going across. So I will say, although I should probably write it out, but I was going to say between silicon and sulfur. Sulfur has a bigger, I guess I'm writing it, bigger EA than S. That's a sideways trend because, I said then S, then SI. Because, oops, BC, not BS, whoops, because sulfur is smaller and has more attractive protons that attract free electrons. My handwriting looks terrible, so I'll read it to you again. So you might have to rewind this one. Sulfur has a bigger EA than silicon because sulfur is smaller and has more attractive protons that attract free electrons better than, Si. All right. Electronegativity. This is almost the exact same thing. It's really weird. Electronegativity is the ability to attract bonded electrons. Okay. So if you're attractive to single people, you might also be attractive to married people. Don't cheat on your wife. That's bad, bad, bad. Don't cheat on your husband. That's bad, bad, bad. Okay. But the idea is exactly the same. As you go to the right, electronegativity increases because you have more attractive protons that attract the electrons, making it easier to attract bonded electrons. Electronegativity increases going up because the size is much smaller due to fewer shells, which makes the attraction of the nucleus greater and makes it easier to attract bonded electrons. Note to score points on why. You talk about a little size, you talk about a little traction, you talk about restating the trend. Okay, so for this one, I'll give you a vertical trend. Oh, I can't read that one, so I'll do this one. I hope that's it. Oh, no, let's pick two that I can read. This is what I get for picking blurry ones. Chlorine and bromine. Okay, I can't read them, but I know what they are. So if I told you that chlorine has a greater electronegativity than bromine because Cl is smaller because of fewer energy levels, so it is more attractive. So notice attractive, more attractive when it's closer. Size is smaller, fewer energy levels. So it's more attractive and attracts bonded electrons better. Whoops, little e electrons. I'll write it out. Electrons better than brr. That's it. First ionization energy. Energy to remove a valence electron from a gaseous atom. Although some people say gaseous. I think either one's fine. All right, so ionization energy is the energy to remove, rip away a valence electron. So what's keeping it from being ripped away is its attraction for the positive nucleus. So as you go, it says increases going left. Did that one say going left? Oh, I just wrote the wrong thing. Increases going right because it's smaller. As you go to the right, it gets smaller. Has more attractive protons, so it takes more energy to remove a valence electron. Yay! It increases as you go up because it's much smaller due to fewer energy levels, and the size makes it more attractive, so it takes more energy to remove a valence electron. Singular. Okay? Simple, 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 simple. Okay? Now, ionization energy has some cool things that go along with it. So that's the basics of first ionization energy. There are exceptions to this trend that you need to get used to. So when we're looking at a periodic table, there are exceptions that occur in this column right here, the boron family, and in the oxygen family. Okay? So as I go through this, notice how boron lower, oxygen lower, right below boron, aluminum lower, sulfur lower. Okay? So then we have potassium, calcium. We know that below aluminum is gallium, gallium lower. Okay? So we have to explain these exceptions. In general, it's low, high, low, high, low, high. But we want to explain these little hiccups. So the boron group is the first element in the higher energy p subshell. So this is the electron that I'm adding, and this is much higher energy. Remember when we looked at the PES? It's higher energy. That means it's less stable. And if it's less stable, it's easier to remove. So if you ever played Jenga, the easiest one to remove is the least stable one. If you're stable, you're being held in place. Okay? That's it. The oxygen group is the first electron that doubles up in the orbital. Electrons repel each other, so putting a second electron, that's me, I'm the second one right there, in the orbital is less stable and easier to remove because it repels a little bit. So it takes a bit less energy to remove it. All right, successive ionization energy and identifying family. Look at this data. So I've got my first ionization energy, I ripped off one electron. Second ionization energy, I ripped off the second electron. Third ionization energy, I ripped off the third one. Fourth one, you get the idea. Okay, so that's what that is. So I go 250, 500, 800. Notice that's pretty consistent. And then 3,500, oh my goodness. So the change here is 250, change here is 300, change here is 2,700. So almost 10 times more. So this note is huge. Or as my dad would say, huge. Element 2, 0 to this is about 600. This is about 700. This is, oh my goodness gracious, that changed about 5,000. See how that's huge compared to the other ones. Okay. Here, 4,000, 4,500, that's a change of about 500. That's a change of about 770. That's a change of about 900. I don't see a big change. Oh, so that means this first one must be my huge one. Okay. There's a huge jump shown for each element. This jump is leaving the small, stable, or small, attractive, noble gas state. Okay. To find the family, I'm going to change that family as huge minus 1 to find the family. Take huge and subtract 1. So the element 1 is huge for the fourth one. So that means in the third family, boron. Let me show you what I mean by the third family. Okay. We are not going to look at the D block. They don't count. This is family 1. This is family 2. This is family 3. This is family 4 all the way up to 8. Okay. So it's from the fourth energy level. So 4 minus 1 is the third family, boron. Element 2 is huge for the third. So it's the fourth family, carbon, right? So you take huge minus 1. Third one, I did that wrong. So element 2 is huge for the third one. So it is the second family, which is the alkali earth metals. Element 3 is huge for the first one, so that's a noble gas. So remember, when you're huge, these guys are small and stable. I'll change to a better color. I hope I'll change to a better color. Draw. Oh no, I think I just muted myself. I did not. I can't. So this is the noble gas. When I leave the small stable noble gas state, I'll start here. If I leave the small stable noble gas state, that is a huge loss. When I start out up here, so let's say I'm starting with I'm doing a 3s guy. So I've got my nucleus, third energy level, right? If I have one here, if I lose one, if this electron gets pulled away, I guess I should draw it the other way if it's getting pulled away. If it's getting pulled away, that means the whole thing is going to get erased. Okay, so now I just got way smaller. Now that I got way smaller, so if I'm looking at this one electron is easy. And then this one would be way harder because it's so much closer. And that's it. We're out of here in under 11. We'll talk more about that in class. So I'll say toodles.